Hi, thanks so much for watching this video. My name is Mark Halberstadt, and this is a run-through of the Senior Design 1 presentation for the NASA Lunar Robotics 2014 electrical team representing Temple University. So what I want to go through is I want to introduce the team, talk about our motivation for the project, as well as the problem statement, design constraints, and then I want to go into our approach towards solving the problems, talk about our prototype, future technical challenges, and also the next steps we will be undertaking in the project. So this is our abstract for the project. My name is Mark Halberstadt. I'm the team leader, and I'm in charge of the autonomous systems. Also working with me is Eric Schisselbauer, in charge of computer architecture and communication, and John Morris is our power electronics engineer. We are advised by Dr. John Helferty of the Electrical and Computer Engineering Department here at Temple. So the motivation for this project is we are going to be entering into NASA's 5th annual robotic mining competition. This is a university-level competition where teams design and build robots that compete with excavating and depositing collected lunar regolith in a simulated lunar environment. So a little bit about why NASA created this competition. NASA pursues a very aggressive exploration program. NASA, famously has sent astronauts to the moon. NASA has sent robotic missions to Mars. NASA is planning on sending a manned mission to Mars, as well as exploring asteroids and returning to the moon. One of the things that can be used to support these long-term deployed missions is the proper utilization of regolith. Regolith, if properly utilized and efficiently mined, can be used to generate fuel, oxygen, water, and certain types of metals, and can really be used to support these long-term deployments of either manned or unmanned teams. So our problem statement is we are going to design and build the power control and communication systems necessary for supporting a robot that is driving through this harsh lunar environment. We are working in tandem with a mechanical team that's working on the same exact project. That team's headed up by Dan Gower, and they're being advised by Dr. Pillapackham in the mechanical department. Our number one goal is that we are building power control and communication systems such that we can support that robot. Our second goal is that this robot should be completely autonomous. We want to be able to just put it down in the arena, essentially push go, and allow it to operate for the 10-minute competition round. Our third goal is that we want to make the most efficient system that we can, such that we can hopefully reduce the size and weight of our battery system and consume minimal amount of power possible. So where we will be competing is in NASA's simulated lunar arena. And essentially this arena has a starting area, an obstacle area containing both rocks and craters, each of which are going to be 30 centimeters in diameter. So we start in the starting area in a random orientation. We have to navigate through the obstacle area, and then we get to the digging area. In the digging area, we have to mine regolith. Then we drive back through the obstacle area, back through the starting area, where there is a collection bin. And we have to deposit this excavated regolith into the collection bin. In order to place in this competition, you have to deposit a minimum of 10 kilograms of regolith. You are supposed to try to excavate and deposit the maximum amount of regolith that you possibly can within a 10-minute competition round. So the way this competition is scored is it's scored based on a point awarding system. Points are awarded for a variety of different criteria, including robot mass, average bandwidth, reporting energy consumed, and dust tolerant operation. Where the electrical team is really concentrating their efforts this year is on achieving full autonomy. Our goal as a team is to earn 800 points or greater in this competition. If we achieve full autonomy, we operate completely autonomously for a 10-minute competition round, we earn more than half of those points. We earn 500 points for achieving full autonomy. And that is our big goal on the electrical team for this year. So our functional design constraints is that we are going to be able to supply power to the robot for a minimum of 30 minutes, and recharging our battery should take no more than 2 hours. we are going to be able to avoid the obstacles, rocks and craters, both of which are 30 centimeters in diameter, and the craters are 30 centimeters deep. We are going to be able to complete, our speed requirement is such that we are going to be able to complete 2 cycles of excavation within a 10-minute time window. Our size constraints are such that we need to fit all of our components into the size constraints provided to us by the mechanical team. And our final technical constraint is that the robot has to be able to locate itself within the arena. We need to have a global location of where we are. For non-functional constraints, the maximum price tag on this project is $5,000. Much of that $5,000 is being factored in from essentially components that have been recycled from past projects. So we are not going to be spending $5,000 this year. The amount we are spending is much less. All of our components have to be very dust tolerant. This is a very harsh, dusty environment. Actually, when we go and put our robot into the competition arena, we all have to put on bunny suits. So we have to make sure that our robot is extremely dust tolerant. For reliability, in order for us to accept our autonomous system, we need to be able to complete a minimum of 20 simulated 10-minute complete competition rounds in order for us to accept that our system is working. Once we achieve 20 successful autonomous competition attempts, we will accept that our autonomous system is working. For manufacturability and modularity, all of the components have to be very standard. In fact, much of what we're going to be constructing our electrical connections from is we're going to be using a Cat5 cable and Cat5 connectors. And then finally, for health and safety, we need a commercial off-the-shelf red button to cut power to the robot, and all of our electrical wiring has to conform to the National Electric Code. So there are 3 separate areas, 3 separate systems that will all be communicating with each other for our control system. There is a main command center PC that will be connected via Cat5 cable to a Wi-Fi router. That's our first system. Our second system is a location system that's going to be affixed to the collection bucket, which will be a Raspberry Pi. This will be connected to the router via Wi-Fi. And then also connected via Wi-Fi will be another Raspberry Pi that is the main control system for the entire robot that's going to be on the robot. This will be connected via Wi-Fi. Also connected to this system will be our Arduino Do that's reading in information from our obstacle sensors and power sensors. And also we will have our motor controllers connected here. So a couple words on a few of the components. Our main control system is going to be a Raspberry Pi. This is a 32-bit ARM-based Linux computer running Raspbian OS that features a 700 megahertz clock. And relatively new to the Raspberry Pi, Oracle has implemented the Java 7 Java development kit on the Raspberry Pi. Much of the software that's been written for this project in the past is written in Java. We're hopefully going to reuse the maximum amount of software that we can that's been written for the project before. So we are really going to be concentrating and writing much of our software in Java this year. Our motor controllers are the Sabretooth 2x25 controllers. The reason that we went with these controllers is because we are able to control these using serial data communication. This provides a very robust link between our main control system and our motor controllers. For our current sensor, we are using the Autopilot 90 amp 50 volt current sensor. This has a shunt resistance of 0.5 milliohm, and it essentially provides analog output for both current and voltage that's scaled for a 3.3 volt analog to digital converter. So our autonomous system is going to be broken down into 4 different subsystems, including a location system, obstacle detection system, navigation system, and actuator control. We are doing this because if we break the autonomous system down into these subsystems, we are able to abstract away a lot of the complexity of the autonomous functionality away from our highest level And we can control our autonomous system very easily with a very simple state machine. Essentially what happens in this state machine is once we start, all we have to do is set a target. We set a target of where we're going to dig to, and once we reach that target, if it's the digging target, once we reach the digging target, we start our collection system. Once we start the collection system, we drive towards what we call the dig finish target. Once we reach that target, turn off the collection system and drive to the dumping area. You notice that there's no obstacle avoidance in this highest level of our autonomous state diagram because all of that is handled by our obstacle detection system and our navigation system. If at any point during this, in this state diagram, either a manual control signal or a stop signal is encountered, the FSM will immediately go to either the manual control or the stop state. So in order to locate the robot in the arena, we are going to be using the Nintendo Wiimote. And essentially what we're using the Wiimote to do is we're using the Wiimote to report the angle at which the Wiimote sees an infrared light beacon that we are going to place on the robot. The Nintendo Wiimote has an infrared camera that has a 30-degree viewing angle. And that 30-degree viewing angle across the x-axis is broken up into 10 full bits of resolution. Essentially, when you divide 30 degrees by 1024, you get 1/34 of a degree resolution at which you are able to report the angle that you see the LED beacon. The Wiimote is reporting the 4 brightest points of light, and we are going to use a separate filtration system to filter out which of the centroids is actually the beacon on our robot. For obstacle detection systems, we are going to be using the Sharp infrared rangefinders, and we are going to be using both the long-range and the short-range rangefinders in order to achieve resolution all the way from 150 centimeters down to 3 centimeters. These are analog components that we will be reading in analog values using a 3.3 volt scaled analog to digital converter, and we will be generating a lookup table in order to use that analog value. This is a curve of data that has been gathered by a long-range sensor. As you can see, the long-range sensor does not provide valid output for distances less than 20 centimeters. Also, this is essentially an obsolete chart. We are going to have to redo this calibration with a properly scaled 10-bit analog to digital converter. As you can see, we're actually in this chart only getting 9 bits of resolution. We do need to redo this. We have a properly scaled analog to digital converter. We are going to redo this testing in order to generate our lookup table. Once you combine all of that together, essentially what you are able to do is report the angle at which the LED beacon is seen. That'll locate the robot in the arena. There's a compass on the robot that will give you the heading angle. The obstacle detector, if the robot location is known, the obstacle detector is able to mark obstacles in the arena. And then an optimal path to a target is computed. So as you can see in this example, in this simulation, the green line represents a path that has been computed by an A-star algorithm that has been simplified using Brazenham's line algorithm that navigates our simulated robot to the dig start target. Okay. So for the prototype, we have been doing much of our testing using last year's autonomous lawnmower platform, and we were really very grateful to have been allowed the opportunity to use this platform. It has helped us out a lot, and we really do have to extend our thanks to Andrew Powell and the Autonomous Lawnmower Senior Design Project for allowing us to use their system, because we have been able to essentially use a lot of the work that they did mechanically in, last year in order to implement our manual control system and also do our to do testing on our autonomous system. So for the technical challenges that we have coming up, one of the largest technical challenges we have is implementing the proper filtration system for our Wiimote location system. Right now, essentially, the way we decide on whether or not we see the LED beacon is we just say the LED beacon is always going to be the brightest infrared source of light. What we are going to be moving to is a system where we are actually going to oscillate the LED beacon on the robot at a rate of 12.5 hertz, transmit a signal to our location system that tells us when that LED beacon is active, and then we're going to use a particle filter to separate the signal from the LED beacon out from the background noise. So that is one technical constraint. Another technical constraint is that we are planning on implementing an obstacle detector particle filter system such that if the Wiimote system fails, we will still be able to get a global location of the robot within the arena. This is important because the Wiimote system is only able to report the 4 brightest points of light. So if it turns out that our beacon is not one of those 4 brightest points of light, we really do need a backup system. The final technical challenge that we are facing is that we need to accurately measure the current on our system if we are going to provide if we are going to get a good idea as to whether or not we can actually shrink the size of our battery and move to a smaller battery system. So we need to make sure that we're accurately measuring the current we consume. Right now, for our power budget, the most costly thing we have are our 2 main drive motors. As you can see in this chart, we're budgeting 10 amps per motor. This is actually a very liberal estimate. Last year at the competition, we measured 5 amps per motor, so this is double that measurement. And similarly, we are providing very liberal estimates for how much both our control system and LED beacon are going to consume, as well as our collection motor and our dumping conveyor motor. All in all, our power budget is set at 40 amps. Our battery has a capacity of 40 amp hours. Therefore, we are able to power our system for 1 hour off of a single charge of the battery. That is double our technical constraint of being able to operate for 1/2 hour. So hopefully there will be room for us to actually shrink the size of that battery, because that will actually benefit us a lot in the competition on the weight requirement for the robot. Our budget, we have spent a good amount of money. As you can see, more than half of the budget is coming from these batteries, which have been used on many Lunabotics projects. A lot of these components have been used on many Lunabotics projects. We have purchased new the Raspberry Pi computer system. This is the least expensive computer system that's been used on a Temple University Lunabotics project in the past 2 years. So we've got some really high hopes for the Raspberry Pi system, and it's been very cost effective thus far. We are coming in at a little over $4,000 right now on our overall budget. For the next steps, by December 21st, kind of before everyone completely leaves, we're trying to integrate in our current measurement system into the testing platform, construct our infrared IR LED beacon, integrate a compass system into the testing platform, and also optimize the Wiimote system such that we can implement it on a Raspberry Pi computer. After that, we want to implement complete manual control of the mechanical team's first prototype. The mechanical team has been working on their prototype all semester. By January 1st, we're going to be supplying them with manual control such that they can accelerate their testing. By January 10th, we are going to be integrating in our obstacle detector sensors to the autonomous lawnmower platform and complete our first full autonomous run using our autonomous testing platform. By January 17th, we hope to accomplish our first fully autonomous run using the mechanical prototype. So the run might not be successful, but we are at least going to attempt one fully autonomous run using the first mechanical prototype by January 17th. These are my references, and that concludes this presentation. Thank you so much for watching, and please let me know what you think in the YouTube comments or by sending me an email. Thanks so much for watching.